Data collection for Doppler processing. With these definitions under our belt, we'll reinforce them with this example, which sets the stage so you can understand what pulses are and how we are processing the data with both Doppler processing and MTI processing. We have echoes coming in an analog fashion, with voltages going up and down. After they pass through the receiver, they go through an analog-to-digital converter, where we sample them one at a time. We metaphorically grab the pulse, see how big it is, and store digitally the number that represents its size. Since the echo coming back is really a vector with amplitude and phase, we must characterize it by two numbers. Much like you would measure a force vector along the x and y axis, we characterize the echo by its real and imaginary parts. The imaginary part isn't non-existent, it's simply at right angles in phase to the real part. We call these the in-phase, I, and quadrature, Q, components of the complex number that makes up the complex envelope of the received waveform. This results into sets of A to D outputs, complex I and Q samples. Next, we fill a memory with these samples. Physically, we send a pulse out, then listen and sample at intervals. Each of these sampling times corresponds to a greater delay after the pulse was transmitted. If we get an echo back from a target, the time it took corresponds to a specific range, calculated as the speed of light times the echo time, divided by 2. So, for each pulse, we fill a matrix with the real part, I, of the sample, corresponding to a specific range. We also fill another matrix with the imaginary part, Q, of the sample. For example, if the 12th sample corresponds to a range of 8.3 kilometers, we store the echo, or noise, if no target is present, in the 12th column of both matrices. We repeat this process m times for each pulse, filling the matrices with real and imaginary components for each range cell. When dealing with MTI processing, the value of m might only be 2, 3, or 4, so the matrix we are filling in memory won't be very tall. This matrix is just a visualization of the computer's memory, with cells representing the range from the minimum distance the radar can detect to the maximum range before sending the next pulse. Now, let's move on to MTI techniques, using the same matrix or memory visualization to understand pulse Doppler techniques. We'll discuss how to take that stored data and apply it to moving target indicator, MTI, techniques to reject ground clutter.